Hello Silicon Pioneers, and welcome to our exploration of the semiconductor cosmos. I'm your host, Semi Sherpa, here to guide you through the intricate world of transistors, conductors, and capacitors, where electrons perform their lively dance and power our modern technology. Today, we embark on a new and comprehensive series focusing on chemical-mechanical planarization, or CMP, and its crucial role in the silicon wafer fabrication process. In this series, we will break down the CMP process into 5 main episodes. The first episode will introduce you to the CMP process and its significance in silicon wafer fabrication. Subsequent episodes will delve into CMP equipment, the mechanisms behind CMP, the chemicals used in the process, and its applications in modern silicon devices. In today's episode, our focus will be on providing a foundational understanding of CMP. This introduction is designed to offer essential knowledge for those new to the world of CMP. Our introductory episode is structured into 4 distinct segments. Firstly, we will examine why CMP is vital in modern semiconductor manufacturing. We will explore its importance in ensuring the performance and reliability of silicon wafers used in advanced semiconductor devices. Additionally, we will cover the brief technical history of CMP, highlighting its development mainly driven by IBM, and how it has evolved to become an indispensable technology in the industry. Secondly, we will explain what CMP is and how it operates. We will focus on the fundamental mechanisms of CMP, particularly the cooperation between chemical softening and mechanical polishing that makes this process effective in achieving the desired planarization of wafer surfaces. Thirdly, we will demystify the CMP polisher. This segment will follow the wafer through the CMP process using popular CMP tools from Applied Materials. We will trace the wafer's journey from the beginning to the end of the CMP process, illustrating how these tools work and their role in achieving the necessary surface characteristics. Finally, we will explore the application of the CMP process in modern silicon wafer fabrication. We will discuss how CMP has adapted to meet the growing demands of device miniaturization and the increasing need for planarization of new materials in contemporary silicon devices. Throughout this episode, we have intentionally avoided complex equations to ensure that our explanation remains clear and accessible. Our goal is to provide a thorough understanding of the CMP process, which is critical for high-volume semiconductor manufacturing. Thank you for joining us on this journey, and we look forward to guiding you through the fascinating world of CMP. Please note that my content is exclusively for YouTube, and any uploads found elsewhere are unauthorized. Each video is meticulously crafted, akin to the precision of silicon wafer fabrication, involving a month-long process with late nights and ample coffee. Discovering my content on platforms other than YouTube is disheartening and impacts my motivation. Supporting the idea of open knowledge sharing should not be mistaken for allowing the redistribution of my content elsewhere. Your understanding in upholding creators' rights is appreciated. Strap in for an enlightening voyage to the essence of the CMP universe. Are you ready to jump? May the silicon be with you. Light speed. Let's start with a key advantage of semiconductor devices. A significant benefit is that as semiconductor devices get smaller, their performance improves. This improvement is encapsulated by PPAC, which stands for power, performance, area, and cost. Smaller devices allow for more chips per wafer, reducing the cost per chip. Furthermore, these miniaturized devices use less power and operate at higher speeds. Think about this unique trait. Is there any other product that becomes both cheaper and better with technological advancements? Very few, if any. This unique feature makes semiconductor devices extremely valuable in modern industries. Chemistry and materials have been crucial in semiconductor technology since the first integrated circuit was created in 1958. Gordon Moore predicted the doubling of components every 2 years, a concept now known as Moore's Law. Initially, technologies like lithography, etch, thin films, implant, and diffusion were essential in converting silicon wafers into microchips. In the late 1980s, chemical-mechanical planarization, or CMP, was invented to address topography issues, which are critical for lithography's depth of focus. Without CMP, it would have been impossible to build and pattern multiple layers from front-end transistors to back-end interconnects. Intel adopted CMP in the early 1990s for the 0.8 micron technology node, which produced the 486 microprocessor. CMP was necessary to planarize dielectric oxide insulating the aluminum metal interconnects. Over the past 3 decades, CMP applications have expanded dramatically, supporting the continuation of Moore's law. CMP is essential not only for improving lithography depth of focus but also for enabling metal interconnect and contact formation through the damascene process. Planarization creates dielectric isolation trenches, insulation plugs, advanced patterning architectures, through silicon vias, and facilitates complex wafer and chip bonding for die-to-die interconnects in disaggregated products. As transistor scaling alone no longer meets performance, power, and cost requirements, complex material and architectural innovations are needed. CMP's novel applications at each new technology node are critical to advancing scaling and supporting the development of more devices. In conclusion, CMP has evolved from an innovative invention to a cornerstone technology in semiconductor manufacturing. It ensures the progress predicted by Moore's law by overcoming challenges related to scaling and complexity. This highlights CMP's vital role in the ongoing evolution and success of the semiconductor industry. Now, let's transition to the topic of optical lithography, focusing on one of its significant challenges, depth of focus, or DOF. In our series on optical lithography, we have emphasized the necessity of improving resolution to create smaller and more precise device patterns. While enhancing resolution is already a formidable task, managing the depth of focus presents an additional layer of complexity. Depth of focus refers to the challenge of achieving accurate patterns of the desired size and shape during the lithography process. To illustrate this, consider the scenario depicted in this slide. In this slide, the top left diagram illustrates the step and scan system used in lithography, where an exposure slit moves across the wafer surface to project the pattern. In our example, 9 DRAM chips are placed in one exposure field. In a DRAM chip, transistors or capacitors for DRAM memory are located exclusively in the cell array area, not in the peripheral area. This situation leads to a significant height difference between the array and peripheral regions. When the wafer surface has uneven topography like this, the critical dimension, or CD, may be within the acceptable range in the array area within a single photoshot field but fall out of range in the peripheral area within the same field. This results in non-uniform CDs across the exposure field, leading to inconsistencies in the pattern. Therefore, the device should be planarized before the optical lithography process. This planarization could be local or global. Local planarization refers to the surface flattening within the array or peripheral area, while global planarization means reducing the step height difference between the array and peripheral area. To illustrate this concept further, consider the analogy of photography. In the photograph on the left side of this slide, you can clearly see all the details of the puppy, while the background appears blurred. This blurring occurs because the background is out of the depth of focus range. In photography, this effect is aesthetically pleasing because it directs your attention to the puppy and not the background. However, in semiconductor lithography, this blurring is undesirable. Blurring in lithography means that we cannot achieve a sharp and accurate pattern across the entire exposure field. Uniformity in patterning is crucial for the functionality and reliability of semiconductor devices. Managing depth of focus is a critical challenge in the production of advanced semiconductor devices. For instance, to enhance resolution, we sometimes increase the numerical aperture, NA, of the projection lens in the optical lithography process. Increasing the NA helps achieve smaller patterns, but it adversely affects the depth of focus. In daily life, you experience a similar effect. When you focus on a close object, like reading a book, the details of the text are clear, which indicates high resolution, but the background becomes blurred. Conversely, when you look at something far away, like a landscape, more of the scene is in focus, which indicates a greater depth of focus, but less detail is visible. In semiconductor device manufacturing, the goal is to keep the entire surface within the exposure field within the optimal focus range during the lithography process to produce uniform and precise patterns. Typically, in the case of the ARF lithography process, a depth of focus margin of less than 60 nanometers is required. This means that the topography in the exposure field should be less than 60 nanometers to ensure precise patterning. Therefore, to make smaller semiconductor devices, the planarization process, like CMP, became essential to sustain Moore's law. This is why CMP is often referred to as a steward of Moore's law, highlighting its critical role in enabling the continued miniaturization and advancement of semiconductor technology. Starting from this slide, we will delve into a fascinating chapter of semiconductor history, focusing on the first application of CMP and its pivotal role in the evolution of device structures. Tracing this history is valuable because it helps us understand why the current CMP processes and equipment are designed the way they are today. Additionally, we will gain insights by indirectly experiencing and learning from the past challenges and technological advancements that have brought us to this point. You might have heard of MEMC, a major supplier in the silicon wafer industry today, which was originally a subsidiary of Monsanto Company. In the early days of semiconductor manufacturing, Monsanto Chemical Company played a pioneering role in developing the world's first CMP process. This groundbreaking technique, now essential for modern integrated circuits, was first introduced at Monsanto's St. Peter's plant, which began producing ultra-pure silicon metal in 1959. Initially, the plant focused on creating silicon wafers for discrete devices like silicon-controlled rectifiers. Dr. Robert Walsh, who joined Monsanto in the early 1960s, was instrumental in this pioneering effort. At that time, traditional polishing methods involved using fine abrasives, like alumina, to smooth the wafer surfaces. However, these methods often left microscopic scratches that became problematic when an epitaxial layer was grown on the wafer. The scratches, while not visible on the bare silicon, would appear prominently once the epi layer was added, compromising the quality and performance of the wafers. Dr. Walsh's breakthrough came somewhat serendipitously. While experimenting with the alumina-based polishing process, Dr. Walsh noticed that the surface quality of the wafers improved significantly over time. He initially thought that the alumina particles were breaking down into finer sizes, which would cause fewer scratches. However, upon closer investigation, he discovered that the improvement was actually due to the gradual incorporation of silicon into the polishing slurry. As the wafers were polished, silicon material from the wafers was being abraded and mixed into the alumina slurry. This unintended addition of silicon particles effectively created a self-regulating mixture, where the abrasive action was modulated by the presence of silicon particles in the slurry. This phenomenon led Dr. Walsh to experiment with colloidal silica, a suspension of very fine silica particles, which was already a product made by Monsanto. The idea was to use a silicon-based abrasive directly, which would inherently be more compatible with the silicon wafers being polished. Colloidal silica, combined with an alkaline solution, provided a dual benefit. The mechanical action of the fine silica particles polished the wafers without causing significant surface damage, and the chemical component of the alkaline solution helped to soften and smooth the wafer surface. This dual action process, combining mechanical polishing with a chemical component, not only maintained the flatness of the wafers but also prevented surface damage. The result was a significant improvement in the quality of the silicon wafers, which was crucial for growing high-quality epitaxial layers. The epi layers grown on these mechanically polished wafers exhibited fewer defects and higher yields, making them ideal for the production of integrated circuits. This historical milestone underscored the importance of CMP in the evolution of device manufacturing, highlighting its role in creating the flawless wafer surfaces required for modern electronics. As mentioned in the previous slide, the initial commercial application of CMP within the semiconductor industry focused on preparing raw silicon wafers. After slicing the wafer from a single crystal silicon ingot, the process involved removing the mechanically damaged surface layer and planarizing the surface. This was essential to achieve a flat, scratch-free surface necessary for fabricating VLSI devices and circuits. Monsanto Corporation pioneered this process, introducing polished wafers to the market in late 1962. Next, let's explore IBM's breakthrough in CMP technology. Shallow trench isolation, or STI, provided the foundational test structures crucial for IBM's initial experimentation with CMP in 1983. This advancement significantly addressed the challenges of planarization. Central to this progress was Dr. Klaus Bayer, an esteemed IBM fellow. His contribution significantly shaped the course of CMP's application in semiconductor manufacturing. Between 1981 and 1983, at IBM's Silicon Wafer Manufacturing and Development Facility, Dr. Baer led a pivotal research initiative focused on refining post-polish wafer cleaning techniques. Dr. Baer's efforts gained international recognition when he received the first Lifetime Achievement Award at the 2015 International Conference on Planarization and CMP Technology. During his award lecture, he recounted the discovery of CMP for device applications at IBM. Despite facing personal and professional challenges, including the sudden resignation of his manager and the tragic death of his lab technician, Dr. Baer persevered. His determination was evident when he observed a trench isolation test wafer displaying a uniform green color without surface scratches, unlike other qualification bare silicon wafers. This observation was a beacon of hope amidst his concerns about the cleanliness and acceptability of the CMP process for device integration. It is important to note that random holes observed in trench areas within the SEM image were due to inadequate glass wetting in trenches measuring 1.5 micrometers in width after the reflow process of lead silicon oxide. Basically, CMP slurry is composed of abrasive silicon nanoparticles. In the 1980s, the idea of using such a mixture to polish wafers for device or wiring layers was nearly unthinkable. Introducing abrasive particles into the pristine environment of a clean room was considered reckless. Within IBM, reactions like "you want to take my wafer and do what?" highlighted the internal resistance to adopting this radical approach. I also recall how my fab manager initially reacted to the CMP process, relegating it to a specialized area and denouncing the abrasive as a source of contamination. Despite these challenges, deploying CMP tools within clean fabrication facilities marked a pivotal shift. The first successful adoption of CMP relied on developing effective cleaning methods for the polishing slurry. Megasonic cleaning, using Triton X as a surfactant, proved to be a breakthrough. This method enabled the removal of polishing slurry from single wafers without causing scratches, addressing significant concerns about the CMP process. Megasonic baths are high-frequency ultrasonic cleaning devices that use sound waves to clean objects with great precision. While primarily used in industrial and laboratory settings, they also have applications in daily life, such as cleaning glasses, dental devices, and jewelry. CMP was developed at IBM-based Technology Laboratory in East Fishkill, New York in the 1980s as a crucial step in integrated circuit fabrication. When research on the CMP process began in 1983, there was significant opposition and skepticism about introducing an abrasive polishing process into the cleanroom environment required for semiconductor processing. Despite these challenges, IBM persevered, and after 3 years, in 1986, they began operating an oxide CMP pilot line. IBM collaborated with several companies during the development of the CMP process. IPEC, now part of Lam Research, provided the equipment. Rode, which was acquired by Dow and later by DuPont, supplied the polishing pads. Cabot provided the slurry. During its early days, CMP was closely guarded by IBM and kept shrouded in secrecy. Development work took place in a lab with restricted access, and even mentioning polishing or CMP outside of a need-to-know basis was not allowed. To facilitate communication within the team while maintaining secrecy, they created names for the processes. For example, the ILD CMP process was called FRED, which stood for Fast Removal of Excess Dielectric. When work began on tungsten CMP, the process was named WILFRED, keeping the spirit of innovation alive under a veil of secrecy. IBM chose to keep CMP as a trade secret, publishing and patenting nothing in those early years. All research and development were conducted exclusively within IBM at East Fishkill until 1988. In that year, IBM agreed to disclose its interconnect process integration scheme to Semitech to strengthen U.S. manufacturing capabilities against the competitive threat from Japan. IBM also decided to share some CMP data with Intel because Intel microprocessors were selected for IBM's PC product line. At that time, the dynamic random access memory, or DRAM, market was dominated by Japanese companies. IBM did not want to rely entirely on foreign suppliers for such a crucial component of its computer system. Therefore, IBM decided to help strengthen a domestic DRAM supplier, micron technology by teaching them about the CMP process. Information about CMP was included in the process for the 4 MB DRAM that IBM sold to Micron Technology. Motorola was introduced to CMP through the PowerPC microprocessor project, a joint venture of IBM, Motorola, and Apple Computer. In 1989, IBM published the first paper on the CMP of oxide films at the IEDM conference. These events initiated the rapid spread of CMP throughout the integrated circuit industry. Thus, the CMP cat was let out of the bag. CMP is a key technology used to create extremely flat and smooth surfaces at critical steps in semiconductor manufacturing over the past 4 decades. Advances in interconnect technology have allowed continuous improvements in making smaller, cheaper, and faster semiconductor devices. CMP is now used for global planarization of surfaces, including shallow trench isolation, interlayer dielectric planarization, tungsten contacts, and metal wiring. The market for CMP is growing significantly as the demand for faster and better electronic devices, such as smartphones and artificial intelligence devices, increases. As shown in left figure, the initial broad application of CMP was in planarizing interlevel dielectric oxide layers. This process addressed the challenges posed by non-planar surfaces resulting from patterned films beneath, which complicated steps like photolithography, metal deposition, and metal etching. The depth of focus at photolithography depends on the illumination wavelength and sets a limit on surface height variation that can be accommodated while maintaining crisp feature definition. To print smaller features, surface topography had to be reduced. The right table outlines the technology node and the year in which key CMP processes were implemented at Intel Corporation, highlighting the critical role of this technology. Gordon Moore, a co-founder of Intel, recognized the essential contribution of CMP to the scaling principles outlined in Moore's law, which has driven the miniaturization and efficiency of semiconductor devices. The application of CMP began with ILD CMP and expanded to include tungsten contacts, STI CMP, copper wiring, high-K metal gates, and FinFET structures. The 1990s saw the formal introduction of CMP technology into the industry, with a surge of new CMP steps introduced around the 0.35 micron node technology in 1995. At the 0.8 micron technology node, ILD CMP enabled complex multi-layer metal interconnections in both logic and memory devices. Later, the 0.35 micron technology node was developed with the introduction of STI CMP and polysilicon CMP in front-end-of-line processes. Tungsten CMP in the middle-of-line and back-end-of-line processes enabled manufacturing below the 0.18 micron node. CMP quickly became essential, particularly for oxide CMP for ILD planarization and tungsten CMP for contacts and vias. Copper metallization technology in the back end of line, known as dual damascene, replaced aluminum interconnects, providing superior conductivity and manufacturability. The diversity of materials polished in CMOS process flows has expanded steadily, reflecting CMP's growing importance. Initially, the planarity requirement was 50 nanometers, but now the industry strives for absolute planarity, 0 nanometers, with a zero defect standard. This pursuit of perfection underscores CMP's critical role in achieving the high precision and quality needed in modern semiconductor devices.
In the late 1980s, IBM pioneered CMP primarily to facilitate the integration of multiple metal layers in integrated circuits. Originally known as chemical-mechanical planarization, it was developed specifically for achieving planarization rather than simple polishing. Planarization is crucial in the formation of metal layers during the interlayer process. For instance, in the transistor wiring process flow, after transistors are created on silicon substrates, a dielectric layer, often silicon oxide, is deposited. This layer, referred to as interlayer dielectric, ILD, or pre-metal dielectric, PMD, fills the gaps between gate and metal 1 layers, inheriting the surface's step height and sometimes exacerbating its topology. The challenge arises during subsequent lithography process, where the step height poses depth of focus problems during high-resolution lithography. Additionally, advancing optical lithography requires tools with high numerical apertures, NA, to print smaller features, but this comes at the cost of a reduced depth of focus window. Therefore, maintaining a flat film surface becomes critical for accurately focusing images across varying surface heights. Before CMP, various techniques attempted local planarization, such as using boron-doped phosphosilicate glass, BPSG, or spin-on glass, SOG. These methods, however, failed to achieve global planarization due to variations in film shrinkage across different pattern densities. This variability caused depth of focus issues during lithography steps, particularly in areas with dense gate patterns where less oxide needed to be filled, resulting in thicker ILD, and sparse gate patterns where more oxide was required, leading to thinner ILD. CMP revolutionized planarization techniques by uniformly depositing silicon oxide slightly thicker than required and then polishing it down until step heights were eliminated. This process ensures a flat surface across the wafer, irrespective of gate pattern density, thereby enabling successive wiring levels. CMP's capability to achieve global and local planarization is indispensable for increasing IC wiring levels, surpassing the limitations of earlier technologies that typically supported only 3 to 4 wiring levels. Initially, CMP faced reluctance due to defect issues such as surface scratching and residual abrasive particles post-polishing. However, continuous advancements in CMP technology have effectively addressed these concerns, establishing CMP as a universally accepted and crucial component of modern IC processing. Now, let's talk about what CMP is. CMP stands for chemical mechanical polishing or planarization. This process involves polishing by using a combination of chemical reactions and physical force to achieve both local and global planarization. Historically, human polishing processes began by polishing stone around 10,000 BC. In our modern daily life, we experience the CMP process directly or indirectly, whether we know it or not. A representative example is brushing your teeth. In toothpaste, there is a slurry with silica abrasive and chemicals. We brush our teeth by putting this toothpaste on a toothbrush to remove the germs on our teeth through the CMP process. Another example is compounding the car coating in an auto shop to remove scratches. This is done by moving the coating from an unscratched to a scratched site by polishing with slurry. Body washing in an Asian-style public bath in the East is also a good example of polishing. This process removes dirt by softening it with soap and then removing it with a towel. You may notice that removing dirt is easier when you take a bath in hot water for a long time. This makes the dirt swell and soften. Basically, all these CMP examples involve chemical softening and mechanical polishing for surface polishing or planarization. Just try to polish your left fingernail with your right fingernail, and you will see that you cannot polish because both have the same material hardness. To be polished effectively, the material to be removed should be softened enough, typically by chemical treatment. In the semiconductor process, chemical mechanical polishing also uses chemical reactions and mechanical forces for material removal. The process involves a chemical reaction for surface softening followed by mechanical polishing to achieve planarization of the wafer surface by removing the deposited film with a slurry chemical. During CMP, a patterned wafer is pressed face down against a rotating pad with slurry being delivered near the center of the pad. The slurry is usually a nano-sized colloidal solution with silica or ceria abrasive and additive chemicals. When the slurry is dispensed by the dispenser arm, it is spread evenly across the CMP pad via a groove channel. This ensures that the slurry is supplied uniformly between the pad and the wafer interface. The CMP pad is primarily composed of polyurethane, featuring internal pores and a rough surface texture known as asperity. The asperity on the pad plays a crucial role in the mechanical grinding of the wafer during the polishing process. Chemical softening is essential when removing various types of films. To illustrate this, let's consider the example of silicon oxide films. The abrasive material used in the slurry is often silicon oxide itself. Polishing a silicon oxide film with silicon oxide abrasive without prior chemical softening is not effective. This is because both the film and the abrasive have the same material hardness. As we discussed earlier with the fingernail example, two materials of the same hardness do not effectively polish each other. Therefore, the chemical reaction that softens the film, like in the case of silicon oxide, is a critical step to ensure successful polishing. When a wafer has a patterned surface with bumps and dips, the chemical softening process affects the entire surface evenly. This means that the chemical reaction softens both the high and low areas of the wafer. However, during the mechanical polishing process, the pressure is applied more to the raised, or protruding, areas. Because these areas experience higher pressure, they wear down faster than the lower areas. This targeted polishing of the high points helps to even out the surface, making it smooth and flat. In simpler terms, while the chemicals soften the whole surface of the wafer equally, the mechanical polishing focuses on grinding down the bumps first. This way, the raised parts get polished away more quickly, leading to a smooth and even wafer surface. To sum up, CMP is a sophisticated technique used to create a flat and even surface on a wafer. It achieves this by combining chemical reactions that soften the film material to a lower hardness than abrasives. This allows the abrasives to mechanically polish the softened film, removing only the surface layer without scratching the underlying layers, resulting in a smooth and planar surface. The basic mechanism of the CMP process involves the mechanical removal of a chemically softened material surface. The CMP process operates by rubbing the wafer, which has a deposited layer to be polished, against a polishing pad. During this process, a slurry containing abrasives is supplied between the wafer and the polishing pad to facilitate friction. As shown in the illustration to the left, pressure is applied to the wafer, and both the wafer and the polishing pad rotate in the same direction, creating friction. The polishing in the CMP process results from a combination of chemical and mechanical actions. The layers deposited on the wafer generally have high hardness, making it difficult to polish them using only abrasives and pressure. This is similar to how you cannot polish your fingernail effectively with another fingernail of the same hardness, but you can easily shape your nail with a harder nail file. CMP works by having abrasives create scratches on the surface to remove material. To achieve effective polishing, the hard layer needs to be softened. This softening is the role of the chemical component in the CMP process. The chemical action softens the surface layer, which is then abraded away by mechanical force. Once the softened layer is removed, the underlying layer is exposed, softened by the chemical again, and then abraded away. This cycle repeats, allowing the polishing to proceed. To explain this in more detail, let us take the example of serious CMP on a typical 300 mm wafer. When CMP is performed for 30 seconds, approximately 51 billion abrasives come into contact with the entire wafer surface. If we imagine that each abrasive forms a single line while removing the softened layer, then 51 billion abrasives would create 51 billion lines, ensuring that the entire wafer surface is uniformly polished, allowing for the removal of the desired material. This immense number of abrasives interacting with the wafer ensures that the entire surface is evenly polished. The abrasives, being part of the slurry, continuously scratch the softened layer, removing it bit by bit. This uniform action is crucial for achieving a flat and smooth surface, which is essential for subsequent semiconductor processing steps. In an ideal case, the softened layer should be softer than the abrasive material to achieve a sufficient removal rate. Additionally, the abrasive material should be softer than the unsoftened layer to avoid creating scratch defects. This balance ensures that the polishing process is both efficient and gentle, maintaining the integrity of the underlying material while effectively removing the target layer. Chemical reactions are a crucial part of the CMP process. One well-known model that explains this softening theory is Kaufman's tungsten CMP model. For instance, when dealing with an oxide film, a basic slurry is used. This basic slurry causes a chemical reaction that softens the oxide film, making it easier to polish away. For materials like silicon, silicon oxide, and silicon nitride, the chemical reaction responsible for softening is called hydration, where a surface layer of silicon hydroxide forms, making it easier to polish. For metal films like tungsten, aluminum, and copper, the chemical reaction is oxidation, which forms an oxide layer that is easier to polish. In summary, CMP involves chemically softening the film to be polished so that its hardness is lower than that of the abrasive. Then, countless abrasives repeatedly and continuously create mechanical scratches to remove the softened layer. This combination of chemical softening and mechanical abrasion is the essence of the CMP process. In order to control how quickly films are removed in the CMP process, it's crucial to grasp the important parameters. The go-to model for this is Preston's equation, developed back in 1927 for polishing glass. Despite its age, it remains widely used for linking removal rates to the downward pressure and sliding velocity applied during CMP. Essentially, the more pressure and quicker rotation, the faster the polishing. While micron-sized abrasives were common for glass polishing, modern semiconductor CMP processes typically use nano-sized abrasives for improved precision control and to prevent scratch defects. CMP involves both mechanical and chemical processes, but pressure and velocity mainly affect mechanical action. Other chemical actions, like those of the pad, slurry abrasive, additives, and friction, are factored into the Preston constant, Kp. Although Kp somewhat accounts for chemical contributions, Preston's equation primarily focuses on mechanical removal without directly considering chemical effects. As seen in the left graph, purely chemical polishing with no abrasive shows almost no effect, while mechanical polishing without chemicals is somewhat more effective. However, CMP with both abrasive and chemicals dramatically boosts removal rates. This highlights the intertwined nature of mechanical and chemical processes during CMP. However, Preston's equation does have its limitations. It doesn't fully address the simultaneous occurrence of mechanical and chemical actions. Additionally, under certain conditions, the relationship between pressure, velocity, and removal rates can be nonlinear, as depicted in the right figure. Thus, Preston's equation is most reliable when chemical effects are minimal, such as in ILD CMP applications. While CMP might seem straightforward on the surface, its underlying mechanisms are incredibly complex and still not completely understood.